How do aerofoils produce lift and drag? The invention of powered flight was revolutionary and sparked a lot of interest around its potential impacts on both commercial and military aspects. The use of military aircraft was prominent in both world wars, but in the Second World War, most aircraft designers were beginning to work with aerodynamics in mind. Aerodynamics was a large factor to their aircraft's success, and R.J. Mitchell, the designer of the Spitfire, which was the pinnacle of British design in terms of aerodynamics. Its sleek, thin, semi-elliptical wing design produced an aerofoil that had low drag and could maintain strong lift. It was also very easy to handle due to this fact, which gave it some of its relatively inexperienced pilots the advantage they needed. To understand how airfoils work in general, a deeper look must be taken into the aerodynamics behind the aerofoils and the importance of angle of attack. The website Airfoil Tools, the X-Foil applet written by Mark Drayler, and a journal titled How Do Wings Work, written by Holger Babinski, a professor of aerodynamics at the University of Cambridge, will be used in conjunction to help explain how lift and drag is created by an airfoil. The Airfoils 2 website is first used to create an airfoil, and a clip of the airfoil can be seen being created using the NACA 4-digit series. Each digit represents a different property of the aerofoil and can be seen to change at the top of the video as the inputs are changed. The first digit represents the maximum camber as a percentage of the chord line. The second digit represents where the chord maximum camber, along the chord the maximum camber is as a percentage of the chord line. The third and fourth digit represent the thickness as a percentage of the chord. The coordinates seen on the right hand side are the same ones that X-Foil applet has stored ready for every single combination of the 4 digits. Here is a video of me using the X-Foil applet to obtain data needed to plot the graphs for lift over drag against angle of attack. This is X-Foil working out the lift and drag coefficients for the respective angles. The graph's axes can be changed to accommodate the data, but all the data that is needed is stored in a separate file in X-Foil. In many textbooks, the most common explanation for lift contains many misconceptions around how lift is produced. The equal transit time explanation goes like this. The airfoil approaches the leading edge of the aerofoil and the airflow in the middle stagnates at the leading edge. The two neighbouring flows keep on moving around the airfoil. One moves along the upper surface and the other moves along the lower surface. The upper surface is seen to cover a larger distance than the lower surface. If the two flows meet up at the trailing edge at the same time after passing the leading edge, the flow along the upper surface must have travelled faster to arrive at the same time as the flow along the lower surface. Then Bernoulli's equation is used to state that the larger velocity flow over the top implies that the pressure is lower in relation to the lower surface. This then creates a net pressure force acting upwards, and an example given is air blown over the top of a piece of paper, causing it to rise. This explanation is true in some aspects, but is mainly incorrect. The equal transit time, no mention of the curvature, and the direct comparison between the two flows, whereas Bernoulli's only describes the change along one streamline. Whilst the aerofoil shown in the video or animation shows that the distance across the upper surface is greater than the lower surface, the difference in length is not required to produce lift. Considering a paper aeroplane where the aerofoil is approximately symmetrical about its chord, implying the upper surface has the same distance across it as the lower surface, there is still lift produced by the wings of a paper aeroplane, otherwise it would just drop straight to the floor. It is the action of drag and a lack of propulsion beyond that of being thrown that causes it to fall down. This means that a symmetrical aerofoil can produce lift, and that lift does not require a difference between the upper and lower surface lengths. The equal transit time assumption can be shown to be wrong with this video from the University of Cambridge. The animation on the top shows how the equal transit time assumption might look if it were true, and the video below it shows an actual test performed on an aerofoil using a wind tunnel where smoke was injected simultaneously into the flow upstream. The flow over the top is clearly quicker than at the bottom, and the two flows do not reach the trailing edge at the same time. So how does the flow above the aerofoil travel faster? The clue is in the curvature of the upper surface, and hence why a curved piece of paper rises when it is blown on. Picture a vortex or a tornado as seen in the GIF, and its concentric circles of flow. If all the flows have the same linear velocity, then the angular flow near the middle of the vortex is going to be very high due to its smaller radius of rotation. This shows that on the inside of the curve, the pressure must be lower than on the outside. This provides the centripetal force needed to keep the flow in rotation. The pressure decreases because the velocity increases perpendicular to the curve as you approach the center of rotation. A simple curved plate can generate lift from this principle of curved flow creating pressure forces. Looking at the diagram, then moving closer to the surface B, the streamlines become increasingly curved. From the curved direction, the pressure is determined to be decreasing as we approach B, the upper surface. The opposite can be said from moving from point C to the lower surface, D, where the pressure is increasing from atmospheric pressure to a higher pressure. Therefore, because the pressure is lower than the atmospheric pressure, because the pressure at B is lower than the atmospheric pressure and the pressure at D is higher than the atmospheric pressure, then the pressure at B must be lower than at D. Due to this fact, that the pressure at D is greater than B, then a pressure difference creates a net pressure force upwards on the plate, which is lift. From this, we can see that any shape that introduces curvature into the flow field can generate lift. Aerofoils work because the flow follows the local surface curvature on the upper and lower surfaces. A thin aerofoil produces curvature in the same direction above and below. This tells us that the pressure along the lower surface is relatively high is high relative to the atmosphere, and the pressure along the upper surface is relatively low. This causes the aerofoil to produce lift because of the suction and overpressure on the upper and lower surfaces respectively. Suction is the pressure force acting away from the surface, and overpressure is the pressure force acting towards the surface. Both sides of this thin aerofoil contribute to the pressure force created. The density of flow lines tells us how much force each side is producing. So the upper surface is producing more lift than the lower surface. This can also be shown using the pressure vector diagrams from X-foil. Above the upper surface, a thick aerofoil produces a similar curvature to the thin one. However, below the thick aerofoil, the curvature is in the opposite direction, which means that there is suction on both sides of the aerofoil. Suction on the lower surface produces a downforce, which means the overall net upwards force produced will be less than that created by a thin aerofoil. The lower surface also has an overpressure region near the leading edge, which will produce some lift. To demonstrate using X-foil, the NACA 9410 aerofoil has been created using airfoil tools. This is a thin aerofoil that has very high camber of 9% of the chord length, and this thin aerofoil creates a high suction force, shown by the length of the pressure vectors. Near the trailing edge of the upper surface, there is some overpressure where the flow has separated separated in the simulation, and the air is recirculating, creating a little bit of downforce. A flow tends to stick to a curved path because there is a shear forces acting on the fluid closest to the surface. Next to the surface, the fluid experiences friction or adhesive forces causing a clockwise moment in the fluid as it enters from the curve from left to right. The fluid also experiences cohesive forces between the fluid particles, which gives it a smaller anti-clockwise moment. Because the net moment is clockwise, the fluid tends towards the surface of the aerofoil. The fluid closest to the surface stops as it sticks to the surface due to the no-slip condition. This causes the fluid above the flow to follow a curved path. This all occurs within the boundary layer on the surface, where the fluid is affected by the friction across the surface. Looking at the red arrows on your right, you might wonder how an aerofoil could possibly fly upside down. Planes just don't do that, right? The truth is that all is required for an aircraft to fly upside down is an aerofoil that can produce more downforce than lift, usually at small angles, negative angles of attack. See the pictures of the symmetrical airfoil NACA 0012. The top diagram is a pressure force vector simulation from X-foil taken at 0 degrees angle of attack. As you can see, the forces on either side are equal and opposite, i.e. an equal amount of lift as there is downforce. As the angle of attack is changed, however, from plus or minus 2 degrees, a net lift or downforce is created. An asymmetric airfoil can also generate downforce, but is naturally going to produce lift at 0 degrees of attack. So usually a more severe negative angle of attack is needed to produce a net downforce for asymmetric airfoils. The angle of attack that the airfoil is pitched at has a strong correlation with the lift produced. Look at the graph on the right. This graph shows the lift coefficient versus the angle of attack for two different aerofoil sections, NACA 2213 and NACA 4213. This graph up until the peak, both graphs show linear correlation. Therefore, generally, at higher angles of attack, where the flow must curve at a much greater rate, the lift produced will be greater than the lift produced at lower angles. This is true up until the airfoil stalls, and the flow can no longer match the curvature of the airfoil. This is represented by the dip in production of lift beyond around 17 degrees. This is because the adhesive forces at the surface of the aerofoil are no longer greater than the cohesive forces or viscous forces, and the flow curves away from the surface. Also, the graph does not cross through the origin. This is because the airfoil still produces lift at 0 degrees of attack. The flow above and below the boundary layer. Above the boundary layer, the flow from the leading edge to the maximum thickness point experiences a favourable pressure gradient where the velocity is increasing because of the decreasing pressure as the flow reaches its maximum curvature and velocity. At the maximum curvature of the aerofoil, the flow is the fastest it can be, just outside the boundary layer. Beyond this point, the flow experiences an adverse pressure gradient as the flow is less curved beyond the thickest point. The flow then slows down above the boundary layer. Inside the boundary layer, the flow's velocity decreases to 0 as you approach the surface due to the no-slip condition. At a point further down from the thickest point, further downstream from the thickest point, the flow inside the boundary layer becomes turbulent, where the overall direction of the flow is parallel to the surface, but the individual flows might not travel completely parallel. The boundary layer grows at this transition point between laminar and turbulent. Beyond this point, beyond the transition point, the flow inside the boundary begins to slow down even more, and the surface is having a more prominent effect on the boundary layer. As you can see, more of the flow within the boundary and just above the surface is slowing down. Eventually, the adverse pressure gradient causes the flow to stagnate and the boundary layer detaches from the upper surface of the aerofoil. The flow is now directed in the opposite direction and recirculates in this area behind the aerofoil called the wake. The separation point creeps forward as the angle of attack is increased. This is due to the fact that the flow is more likely to become turbulent at a quicker rate. Here are some of the graphs produced from the data simulated by X-Foil. The graphs show the lift-to-drag ratios against the angle of attack. The peak points on the graph indicate the angle where the aerofoils produce the most lift for the least amount of drag. For the aerofoil with the 2% maximum camber, the angle is 7.5 degrees, and the aerofoil with the larger maximum camber of 4% has a steeper angle at 10 degrees of attack. The more curved the aerofoil is, the more lift the aerofoil produces. At the maximum point, the aerofoil can produce its maximum range, and should the engines fail for the respective aircraft that these aerofoil have, the angle will provide the biggest range to altitude ratio when gliding. Stall occurs when a plane is flying at low speeds and at high angles of attack. The speed and angle varies upon the weight of the aircraft, where the centre of gravity acts, and the load factor. This is the centripetal acceleration experienced, usually expressed as a multiple of the acceleration due to Earth, or G force. Stalls initially cause some loss of control as the flow detaches and the wake travels over the ailerons, causing them to be ineffective. There is a loss of lift, and due to the moment created on the wing, the nose tends to pitch downwards. A full stall can cause serious damage if the plane does not recover, where a spin can occur and be fatal if the aircraft is too close to the ground. To avoid a full stall, several safety devices and wing characteristics have been engineered, the first of which is an aerodynamic twist, which can be seen on the top right. The aerofoil at the root of the wing is angled at a greater degree than at the tip. The picture shows a very exaggerated version of this twist, where it's usually between 2 degrees twist. This gives the effect of cold washout, where a wing is deliberately designed to reduce the lift distribution across its wing. The angle or lift at the root will be greater than at the wingtip, but this also means that the root will stall before the wingtip does. If the root stalls, the plane will buffet in the wind, indicating to the pilot that the whole wing is just about to stall. So before the full stall can occur, the pilot has a chance to use his ailerons, which will still respond because the tips of the wings have not stalled. Another method is a stall strip, which can be attached to the leading edges of both wings on an aircraft. These strips are triangular in cross-section and encourage the wing to stall at a certain spot on the wing. It works by creating a sharp angle of attack between the relative wind and the angle of the triangle. This is relatively higher than the angle between a curved leading edge and the straight edge of the triangle. This causes the boundary layer to become turbulent sooner. Like the twisted wing, the root stalls first, then the wingtip. Another method commonly applied to swept wing aircraft are wing fences, and these are flat plates protruding from the upper surface parallel to the flow. They usually wrap around the leading edge and continue to the trailing edge. here is a picture shown of the MiG-17 aircraft in the bottom right. And these fences obstruct the flow that is deflected outwards by the angle of the swept wing. These fences obstruct the flow that is deflected outwards to the wingtip whilst approaching stall speed. And at the wingtip, if the fences weren't installed, the flow can almost all be spanwise. So the flow will be travelling from the root to the tip, instead of normally as from the trailing edge to the leading edge flow. The flow of air over a swept wing usually causes a pitch down moment. This is due to the centre of gravity acting in front of the centre of lift on most swept wing aircraft. However, if the wingtip stalls, then the opposite is true. The aircraft tends to pitch up, causing a more severe stall, which is why wing fences are necessary to prevent stall. This was an explanation of how aerofoils work. Thank you for listening.